devices that are reported uh, in this domain. Specifically, if you want to go for beyond CMOS thing, what are the all possible options? Which option will be preferred and why? And how can we start doing research in this domain? Because if it is the faculties are the target audience, we should focus more on the research aspect than the basics aspect. Okay, so this is my talk outline. I'll be starting up with the transistor. What is it, how does it work, what is its expectation, how should we go ahead with, then what is the roadmap for this beyond CMOS devices, what we are trying to achieve, and how can we achieve our how can we supersede the existing CMOS devices by using those innovative approaches. Then why there is a need to go for beyond CMOS, what are the alternative devices. Basically, I'll be covering these four devices: tunnel field effect transistors, impact ionization MOSFET, negative capacitance FET, and carbon nanotube FET. All these four approaches I have worked with along with my PhD scholars, so I'm pretty much sure about their simulations, about their challenges, about their potential. I can cover in depth. Apart from these four aspects, there are n number of other things like valitronics is there, spintronics is there. I have partially covered the spintronics as well in my research aspect, but I have not kept it as a part of today's talk. Probably sometime or the other we can talk about the spintronics, but today's discussion will be limited to these four devices. What are their key potential aspect, what are the key challenges, and how can we start doing research in these particular devices things. Then we can then I'll give you a glimpse of other available potential options that are very much there in the literature, but I myself have not worked on it, so I'll be simply touching it. I will not be covering it in much details. Okay, so roadmap flow. What does it say? We are talking about the CMOS industry. We are talking about the silicon industry. We are talking about the transistor things. So today it is very tough to think about an human life aspect which doesn't have electronics in it. Be it an automatic vehicle, be it your laptop, be it your palm top, be it your cell phone, be it your medical diagnostic appliances, instruments, communication appliances, instruments, even the renewable energy things. If it is automated, then also it will be having a transistor at its backbone. So we are affecting every single aspect of humans' life, right? Then why there is a need to go for green electronics? I have written it as CMOS industry. As you can see, there every single aspect of our day-to-day life is now being controlled some or the other way. It is being controlled by the transistors. Then why there is a need of green electronics? We know electronics, a low powered switching. If I am making a circuit using a low power switching transistor, I call it as electronics. If I make that switching at a higher energy level, I'll call it as electrical. But why there is a term green associated with it? Green electronics. If you know, we studied the green technology. If you know, we study the organic thing. Wherever this green thing comes, it means it is very much friendly to your ecosystem. Which electronics is friendly to your ecosystem? You have heard that electronics is causing this much bad to the ecosystem. It is resulting into huge electronic waste. It is resulting into huge power dissipation. Then what do you understand by the green electronics? Why there is a need of the term green? Anything which is beneficial, anything which is beneficial or supported to ecosystem. How can your electronics support your ecosystem? If your electronic is having zero power dissipation, In that case, you can call it as green electronics. But practically, can there be any transistor which can give you a zero power dissipation? No. Ideally, there can be a transistor which can have a zero power dissipation, but practically, zero power dissipation is something that is very far away from realization. Then what should be our approach in this green electronics thing? You should be focused on minimizing this power dissipation. So all these four transistors that I'll be covering in my talk, they all be based on the power minimization aspect. Right. Now to start with transistor, first thing first, what is in transistor? As we all of us are faculty some or the other way, then we know that to start with the transistors, first thing we tell to our students are transfer of resistance is called transistor. So you are transferring a low resistance part to a high resistance path so that you can get a voltage amplification, and this is the very first starting of your transistor. What is your expectation from a transistor? If you want your transistor to work as a switch, then it should have absolutely zero current when it is off, or as low as very low off current, and very high on current, and very low off current. Then you call it as ideal switch. So if you want your transistor to behave as a switch, it should have highest possible ion to I of ratio. And if you are plotting the same thing, this was the case with the ideal transistor, but ideal things does not exist. So from ideal we are going to the practical one. You can see practical one, although the current value is significantly high, but it is not infinite as it was the case with the ideal switch. Then you are plotting the same VGS on the logarithmic scale. You'll see that the I of current is very low, of the order of 10 to the power minus 12, minus 13, and minimum ion current that you need for an electronic switching is of the order of 10 to the power minus 3 milliamperes. You at least need a current of the order of milliamperes to uh, let your circuit work efficiently. So we have started from a transistor concept, transistor thing. Ideally, if you tell about the ion values, it is the ion saturation, and there is a quadratic relationship between the overdrive voltage and the current. Right? What is your two aim motives? To achieve as high ion as possible, and at the same time you want to have a lowest possible of current, right? Then why there is a need of beyond? As you could see that this 1.5 hour of your life you are devoting towards beyond CMOS. So why you need to go for beyond CMOS, that should be clear to you. So back in 1965, Moore has given us a statistical law. It was, what did he say? He says that the number of transistor on each IC is doubling in every 2 years or 18 months period. So what was it? A technological law? No, it was a statistical law. He has simply plotted the number of transistor in each year, and then he extrapolated that graph and predicted that yes, if this thing holds good by 1975, this will be the number of transistor on your same area of IC. But why we followed this statistical law? Moore's law was not based on any physics. Moore's law was not based on any technology. Then why are we still, I won't say we are still following this scaling things or the Moore's law, but still it had it controlled our semiconductor industry for more than 4 to 5 decades, because it was properly backed by the economy. If the number of transistors are doubling on an IC in every 18 months, what is happening? Functionality is increasing. Earlier you were having 100 transistors, now you are having 200 transistors. So no doubt the functionality of an IC will be increasing. And at the same time, if the functionality is increasing, what is the effect on its cost? It is getting more cost effective, isn't it? If you are able to get the enhanced functionality at a lowered cost, it is being very much backed up by the economy, right? I think this card. Let me check whether I am still audible or not. I don't know why people are raising hand. In I think they might have some question. Let it be. First, let's finish with yes. So this Moore's law is controlling the semiconductor field for 4 to 5 decades, for more than 40 years, because it was being uh, it has started in 1965 and we are in 2024, but still we are talking about it. Unfortunately, we lost him last year, but still we are talking about his law. How important this law was. What did he say? So in IC industry, silicon IC industry, if the number of transistor has to be increased, then the distance between the two elements, means pitch size, has to be reduced, functionality has to be increased, and for more than 45 years, the price of the memory and the gate has dropped to 100 million times. So if the price is dropping and the functionality is increasing, so economists or the industrialists are favoring this law. Technologically also this was very good. Then why we need to think beyond CMOS? If CMOS is that much good, do we need to go beyond CMOS? That is what we'll try to see, why we want to go for CMOS. Was good. It was good because it was economically favored, it was increasing the functionality. Then why we need to go for beyond CMOS? CMOS is good, but still we are going beyond CMOS. So my question is, in next 15-20 minutes, I'll try to go address why we need to go beyond CMOS. Okay. Then I'll tell you what are the options to go beyond CMOS. Okay. So why beyond CMOS? The very first thing is threshold voltage roll off. What does it say? It says threshold voltage. If you remember perfectly, because all of us are faculties, your threshold voltage is never a function of channel length. So whatever, whether your channel length is 5 micron or your channel length is 5 nanometer, the threshold voltage should be same. Because if you talk about the MOS device physics, you won't find any relation between VTH and channel length. But when you are going for scaling at lower than 180 nanometer, what did you see? You see 180 nanometer. What did you see? You started with a 1 micron. Please check. Here the channel length or gate length is increasing. I'm not sure what is happening in that place. If someone is raising hand, I'll address all of your questions at the end of this talk. But as I'm sharing my screen, I might not be able to see your raised hand or your typed questions. I'll be addressing all those questions at the end of this talk. Okay. Right. So very first thing that I'm trying to explain you is threshold voltage roll off. Your threshold voltage happened not to be a function of channel length, but what is happening when you are going beyond 180 nanometer. If you are going beyond 180 nanometer, please see. When you are at 1 micron technology, your VTH was constant. It is not playing as a it is not changing as a function of channel length. But when you are going below 100 nanometer, please see, your threshold voltage is, practically you are seeing that, practically you are seeing, observing that your threshold voltage is reducing with decrease in channel length, and this decrease is very much dominant at below 100 nanometer, and it is also dependent on applied VDS. Please see, in first case where the graph is the black one, applied VDS is 50 millivolt, and when I am talking about the blue case, the VDS applied is 1 volt. So where VTH roll off is more, where VTH is changing more, in the black case or in the blue case? My VTH is changing more in the case black case, or in the case where my VTH is changing more when my VDS is high. Higher is the VDS, higher is the change in threshold voltage. So threshold voltage is acting as a has started acting as a function of channel length, as well as it is also acting as a function of applied VDS. Till now, we do not know any physics based equation which says that your threshold voltage is a function of channel length. But now, what is happening? Now you are seeing, practically observing that your channel length, your threshold voltage is reducing with respect to decrease in channel length, and this threshold voltage reduction is directly proportional to the applied VDS. If you are applying a higher VDS, then your threshold voltage is lowering at a higher pace. So this is the practically observed thing. But why is it happening? What is the physics behind? So let me explain you. Please see. I am comparing the two device, long channel device and short channel device. Long channel and short channel device means this the gate length is higher. Here the gate length is lower. It means in first case the source and the drain is far from each other. In second case, what is happening? In second case, your source and your drain, they appear to be closer to each other. So what is happening? It is simple. If you see an analogy, if you are standing in a queue and six people are standing in a queue, okay, and the distance between the six people in first case is 1 feet, 1 feet, 1 feet, 1 feet, right? Now consider the second case. Six people are standing in the queue, and distance between the two person is now zero point 0.5 feet, zero point 0.5 feet, zero point 0.5 feet, right? In which case, if you are pushing one person, in both the case with the same energy, you are pushing a person with the same force, where the distance between the two people is 1 feet, and in second case the distance between the two person is zero point 0.5 feet, where your thrust is more, where you are expected to create a more uh, means pronounced aspect, case where those people are very closely placed. If two people are very closely spaced, if you are pushing one person, that force will be easily transferred to the other one. But if they are standing at a distance with each other, if you are pushing this person, there is a finite chance that that force might not be transferred to the other person, right? Similarly, in long channel device, the source and drain are not in close proximity to each other. If you are applying any bias at the drain side, it is not reflected at the source side. But when you're talking about a short channel device, your source and drain are in very much close proximity with each other. So if you are applying any bias here, if you are applying 1 volt, say here, any bias here, then it will be, what will happen? It will affect your potential barrier at the source side also. So it is not only threshold voltage roll off, this can be also termed as DIBL, drain induced barrier lowering. So this is the very first reason While people started thinking of going beyond CMOS. Ideally, VTH is not channel length dependent, but practically it is dependent on the channel length. And the channel, if the channel length is decreasing, my threshold VTH roll off is also increasing, and it is also dependent on the applied bias. So yes, this might degrade my net circuit performance. So that is why people, okay, fine, let us think or let us try to get something which is beyond CMOS, right? Then the short channel effect. There are other SCEs also, although DIBL is also SCE. There are other different SCEs responsible to think for to motivate us to go for beyond CMOS. You can see in this simulation curve. Please see. You are talking about one transistor, and its channel length is 50 nanometers. So the distance between source and drain is said to be a constant 50 nanometer, right? Now, in for the green case, the applied VDS is 0. If the VDS applied VDS is 0, this is the potential barrier between the source and the channel. This is the potential barrier. Now take the second extreme. If the applied VDS is 1 volt, the purple one, the cyan win, here the applied VDS is 1 volt, and applied VDS is 1 volt, although you are applying VDS at drain side, but it is also lowering the barrier at source side. It should only, if you are applying something at the drain side, it should only affect the drain. It should only affect the drain, but it is also affecting the source and the channel barrier, and this is called as short channel effect, SCE, right? Okay, fine. What is this? Is the cause? What is its effect? What is its effect? The cause is low channel length, and it is resulting into lowering of your potential barrier. Okay, so what is happening after it? What is the effect of it? Please see. As an effect of it, your drive current is at a constant voltage, say 10 to the power minus 3. But what is happening? Your off current. In first case, your off current is somewhere at 10 to the power minus 10. But this off current is increasing exponentially. And what will happen to if your off current is increasing exponentially? What did I say at the starting of this talk? For an ideal transistor or for a good transistor, what should be the case? For a good transistor, ion to IF ratio should be as high as possible. But if my ion is same and IF is increasing exponentially, my ion to IF ratio is decreasing exponentially, it means it is degrading my transistor performance. Now, what is happening? What are the other causes? Other causes are P oxide. P oxide is also, if channel length is decreasing, LCH is decreasing, my T oxide is also decreasing. If T oxide is decreasing, then what will happen? There is a finite chances that my gate gets shorted with channel. And if my gate gets shorted with channel, what will happen? Entire gate control mechanism is lost. And if my gate control mechanism is lost, then there is a serious reliability issue for my transistor. So this is the third cause of going beyond CMOS. Now please see, there is a very good example of, here. They are comparing three transistors. Transistor 1 with channel length 70 nanometer, transistor 2 with channel length 50 nanometer, and transistor 3 with channel length or gate length 30 nanometer. If you compare them, here 70, 50, 30, the channel length is decreasing linearly, right? But please see here, they are plotting all of these graphs are simulation based. Why am I clearly distinguishing this simulation based? Because many of us, our faculties will have to give some or the other project to our BTech scholars so that they learn something new. So these simulation, small simulation exercises can be given to our UG students so that they learn these basic concepts of devices, right? Please see, they are plotting current IT versus VGS for 70 nanometer, 60 nanometer, 50 nanometer, 45 and 30 nanometer. The channel length is reducing. Here the channel length is reducing linearly. But please see, the leakage flow or the leakage current is increasing exponentially. And it is not only increasing exponentially, this leakage flow is increasing exponentially for one transistor. Now if you talk about the VLSI IC, that there are billions of transistors in a single IC, right? Then what will happen? This cascaded effect of increasing this leakage flow on the net IC performance will be very lethal. You cannot work with so high leakage transistors. So these high leakage is the major culprit why we need to go for beyond CMOS. Apart from this, there are n number of other scaling issues. Considering this, I am talking to faculties. These things you are aware of this RDFs, you are aware of this quantum confinement effect, then your scattering reasons, poor subthreshold things, and all these things collectively resulted into the need for going beyond CMOS. Okay. So what are the things? VTH is no more following scaling. Your mobility is not at all constant. Your drift velocity is also getting saturated at VSAT value. Your IOF is also increasing, and this is what you have learned into your those simulation exercises. Then your process variation effects are there as you keep on reducing the channel length, then the lithography equipments that you need is of high price, then power dissipation, high heat is getting dissipated, then you need to design a cooling circuit for the same, right? So your mobility is also not constant, velocity getting saturated. All these things resulted into a bottleneck, and that bottleneck has motivated us to go beyond CMOS, right? So this is how our research till nanoscale FET is here. Industry is working very fine. Good. For 14 nanometer channel length, if you are talking about 14 nanometer channel length, fully depleted SOI is perfectly fine. But if you want to scale it down beyond 14 nanometer, then what will happen? You need to search for different new materials. These materials can be graphene, these materials can be carbon nanotubes, or you can talk about silicon, germanium alloys. There are various other material aspect that has resulted you to scale it down below 14 nanometer. Otherwise, for 14 nanometer, your FinFET is also working fine. We are having our all those semiconductor technology which is based on FinFET. It is working fine at for 14 nanometer node. If we are talking about FDSOI is working fine for 22 nanometer. And if you are talking about FinFET, it is working fine for 14 nanometer. Various practical products are there based on 14 nanometer FinFET. It was very well there back in 2017 itself. But if you want to scale below 7 nanometer, you need to think about the nano sheets, nano ribbons, new materials, new geometries. Then the strain engineering means making alloy of silicon and germanium. Various 3D process control things should also be addressed. This is what ITRS has predicted back in 2020, and we are in 2025. So, can I say that this chart is very much updated? No, we are still lagging by 5 years. Some or the every single year, ITRS comes with its own new roadmap or own new guidelines to guide the research path of this beyond CMOS devices. Then another very crucial term comes is sub-threshold slope, SS. Why I need to have a sub-threshold slope? What is sub-threshold slope? Why it need to be reduced? And what is the minimum possible sub-threshold slope that is achievable by using your conventional CMOS technique? If you are talking about sub-threshold slope, simply the slope of this log ID versus log VGS. The inverse of its slope, log D log ID over VG. Inverse is called as subthreshold slope. So ideally, if we are talking about the conventional MOSFET or the typical CMOS, the minimum possible subthreshold slope cannot be lowered below 60 millivolt per decade. But if you want to reduce the eye leakage, one very strong thing that exists is you should reduce sub threshold slope, SS. Why I want to reduce SS? Because if I reduce sub threshold slope, eye leakage is also reduced, and if eye leakage is reduced, my net short channel effect or my all those detrimental effect because of scaling down can be taken care. So I should reduce sub threshold slope. Yes, this is one of the very uh, interesting slide that I always put to, because if I am uh, researching something which is not making money or which is not able to save money, it is of no good use. But this slides tell us that if I am able to make my transistor a green transistor, it means its power dissipation is reduced to almost zero. It means, please see, there are more than 40 products in our daily household. All of us are having particular thing was done in an American household, but even in India, we are using all those things, all those appliances. We are using a mobile phone charger, desktop computer, laptop, LCD, CRT, set-top box, digital cable, VDR, then DVR, then cable modem, game console. All of these are being used. And please see, they are also consuming power when they are in sleep mode. All these appliances are there in our household, and they are also consuming some or the other power, low or the more power, even if when they are in sleep mode or they are off from remote. So we are paying 10% of our electricity bill for the energy that we are not even using. So if I am able to go beyond CMOS, what is going to be the case? If I am able to go beyond CMOS, what can help me? I can also save my electricity bill. How much? By at least 10% of my net electricity bill. Right. So what are the approaches? How can I go beyond CMOS? Till now I talked about why I need to go beyond CMOS. Then I'll tell you what are the techniques to go beyond CMOS. There are four majorly available techniques if you want to go for with respect to the devices approach. There are four charge-based devices approach that are coined in literature for going beyond CMOS. Tunnel field effect transistor, first. Impact ionization MOSFET, IMOS is the second. Negative capacitance FET or NC FET, or you can also call it as ferro FET. This is the third approach. Then carbon nanotube FET, CNT FET. This is the fourth approach. There are four probable approaches to reduce your subthreshold slope, and if my subthreshold slope is reducing, inherently it is also reducing my leakage current, and my leakage current is reducing. It means my short channel effects are well taken care of. So let me start up with the very first device, tunnel field effect transistors. Classically speaking, my electron should not be able to cross a potential barrier unless until I do not give it an energy higher than the energy of this energy barrier. But you know, classically, if an electron is bombarded on an energy barrier, if its energy is lower than the energy barrier, it should be 100% reflected back. But is an electron your classical device? No, electron is your subatomic particle, and for electron, your classical physics doesn't work, your quantum physics works, and quantum physics says that my electron shows a dual behavior. Sometime it behaves as a particle and another time it behaves as a wave. And when my electron is behaving as a wave, and if it is incident on a potential barrier, although this wave is having lower energy than this potential barrier, but some part of this wave will be transmitted across the potential barrier and some part will be reflected back. Although the energy of this electron wave is lower than the energy of the potential barrier, but still it will manage to get transmitted. And this tunneling mechanism is used to make a MOSFET, and it is called as tunnel FET, TFET. Okay, so this is the classical case. My MOSFET, here the source and the drain both are of same kind of dopants like N plus and N plus, but in TFET, if source is P plus, drain is N plus. If drain is P plus, source is N plus, and vice versa. What is the basic governing mechanism of it? Basic governing mechanism for MOSFET is, for the case of MOSFET, the transmission takes place across the barrier, over the barrier. It means you should have at least energy equal to the potential barrier, then only you will be able to get some electrons collected at the drain side. But when you're talking about the TFET, it is through the barrier, although the electron is having energy lower than the potential barrier, but still, as this tunneling barrier width, the width of this tunneling barrier is very low, say 1 or 2 nanometer, then your electron managed to tunnel through this barrier, and their electrons will tunnel from source to channel, and it will get connected at the drain side. This is the very simple mechanism of your tunnel field effect transistor. And if I talk about in terms of the applied bias, when VDS applied is 0, the tunneling barrier here the tunneling barrier is wide, and no electron managed to go from source to the channel side, and that is why your current is 0. But when you increase VGS, this barrier is reducing, width is reducing, and if it is high, in that case more number of electron is managing to go from source to the channel side, and you are getting more current, and this is what is happening when you are applying a VGS equal to 0.4 volt. Then what will happen if I am applying a negative bias? In that case, the tunneling will take place from drain to channel instead of from source to channel. If you are applying a negative bias at the gate side, you will get a tunneling of electron in reversed direction. That is called as ambipolar transport. Tunnel FET gives you an ambipolar transport behavior. Okay. So many people come up with the various options of tunnel field effect thing. Then in order to enhance the performance of tunnel FET, what people think that, okay, fine, replace the source material with some low EG thing. Energy band of this material, if the energy band of this material is reduced, then the tunneling probability will be increased and I'll get a higher current. So instead of making the entire TFET from silicon or homojunction tunnel FET, people opted for heterojunction tunnel FET. So this, if you want to start doing your research in TFET, some people comes to, okay, fine, I want to do research in TFET, and they are making, still they are making TFET with the silicon. Trust me, it will not be published anywhere. So first thing what you get, if you have, you want to work on TFET on in 2025, then you should work on some heterojunction kind of TFET. You should then, can I make it this source as, instead of germanium, can I make it as some higher EG material? No, the source EG should be as low as possible to give you a higher ion current. So this is the chart prepared by one of my PhD scholars during her PhD thesis. Yeah, this simple one slide gives you the entire state of art of tunnel field effect transistor. What does it says? What is the merit of tunnel field effect transistor? It is immune to short channel effect. It gives you a lower subthreshold slope SS. It needs lower supply voltage, and the leakage current is lower. What are the drawbacks? There are majorly three drawbacks of TFET. Its drive current is low, it gives you an ambipolar transport, and basically the device architecture is asymmetric. What does it mean? If the source is N plus, drain is P plus. If the drain is N plus, then source is P plus, and vice versa. So it is an asymmetric device. So there are three major drawbacks of TFET. And if you are working on TFET, you just start with working. If you want to reduce the ambipolar current, these are the approaches. If you want to increase the ion current, these four are the established approaches. If you want to work on the asymmetric thing, these three are the established approaches. This, it is very finely represented in the PhD thesis of this girl. But majorly, if you as a faculty want to start give this thing as a topic, research topic to your scholar, you can tell them to take this thing as a reference and start doing their literature survey, because this literature survey was done in 2019 and she got her degree in 2022. So you can still get 2 years are still there. So if you do more exhaustive literature survey, you might get some more approaches. Now, the second device of the series is impact ionization, or IMOS. The structure wise, TFET and IMOS both are same. If the source is P plus, the drain is N plus. So what is the difference between the IMOS and the TFET? Please see. In TFET, the gate was the entire this area, but in IMOS, the gate is semi-overlapped. Gate is partially to at the drain side, it is not there at the source side. Why? Because it will give it a intrinsic region. Intrinsic region. What is the effect use of this intrinsic region? In this intrinsic region, impact ionization, IMOS. What is impact ionization? All of us, if you remember it, impact ionization is basically a chain reaction. One electron is generated, then it will gain a kinetic energy and it will create an EH pair. Then these electron and these hole again gain a kinetic energy and result into another EH pair. Then again these EH pairs will accelerate in the intrinsic region, get kinetic energy, and it will again result into more EH pairs. So it is a chain reaction. So if impact ionization is chain reaction, then one thing is pretty much clear, that your ion will be very high here. The second thing has to be clear is, if the electric field needed for impact ionization is high, its drive voltage is also very high. Okay. So impact ionization is also a symmetric device. Impact ionization gives you a higher drive current. Impact ionization needs a higher supply voltage. These three things can be inferred from this slide. Then the fourth thing that is very crucial is, impact ionization it is very tough to get a reversible and safe area of operation or impact ionization. That is why what is happening? That is why the reliability of impact ionization is lower. So major issue with C, operating voltage is very high, -5, -4, -3. But the drive current is also very high, of the order of 10 is power -3. This is exactly what we needed. Sub-threshold slope is very low. Instead of 60 millivolt, you are getting 10 millivolt per decade. But what is the major issue here? Reliability. You are getting a very low reliability device. That is why you are not able to mature this IMOS technology. So if someone comes with the four approaches, at least we know about the two TFET and IMOS. Which will you prefer and why? Both TFET and IMOS are asymmetric device, but TFET is operating at a lower voltage, so it is a low power device. Secondly, the TFET gives you a lower subthreshold slope, and TFET gives you a reliable behavior. Whereas for IMOS, reliability is low. So whatever be the performance of that device, if its reliability is low, you are not expecting to use it for day-to-day purpose. Now coming to the third device of the series of four devices we need to cover. This is the very third device, and I tell you it is the most potential device. Why am I saying it as most potential device? Because please see, FET, negative capacitance FET, NC FET is a symmetric device. So if your source is N plus, your drain is also N plus. If your drain is P plus, your source is also P plus. So it is a symmetric device. So it is same as MOSFET. But how it is different from MOSFET? Instead, please see, this is silicon. Above silicon you have a high K metal, and above this you have a gate metal. So this up to this place, this is a common FET or common CMOS. But after this, what is you are having? You are having a ferroelectric material, and above this ferroelectric material you are having a metal layer, Fe and metal. So this is making it a negative capacitance. So this concept of negative thing, what is capacitance? What is resistance? Basically resistance is obstruction to the flow of current. You call it as resistance. What is capacitance? The ability to store charge in terms of electrostatic field. If you are storing a charge in terms of an electrostatic field, you call it as capacitance. Can your capacitance be negative? If you are what is the capacitance? You are having metal plate 1 and metal plate 2. If you are storing some energy between these two metals in the dielectric between these two metals, you call it as capacitance. But can this capacitance be negative? No. Can resistance be negative? No. But your differential resistance can be negative, or your differential capacitance can be negative. A negative capacitance behavior will not be stable. A system having only negative capacitance will not be a stable system. So what is negative capacitance means? Negative capacitance means like you are having 1 volt here and you are having a ground here. Okay. Ideally, what happens to this capacitance? The electric field start from positive and set negative, and this is the positive C behavior. So if you are having a 1 volt here, there will be some loss here, and you whatever be reflected here or mirrored here will be lower than 1 volt. This is the classical capacitance behavior. But for negative capacitance thing, if this is metal plate 1, this is metal plate 2, you are having, instead of having a dielectric, here you are having a dielectric medium. But here, instead of having a dielectric medium, you will have a ferroelectric medium. What will happen to this? What will happen to this? These ferroelectric materials are having dipoles. So these dipoles, electric dipoles, are also getting aligned in the direction of, it is also getting aligned in the direction of electric field. So if you are applying a 1 volt here, this 1 volt plus some bias because of this ferroelectric material. So here you will get a higher potential, say 1.1 volt or 1.2 volt. So this particular behavior is called as negative capacitance behavior. And this particular idea is used to improve the MOSFET behavior. And this particular kind of MOSFET is called as NC-FET. So this is the silicon capacitor, this is the oxide capacitance, and now above this oxide you are also using a ferroelectric material. So this is the capacitance because of the ferroelectric material, and net capacitance, the net system capacitance will be this ferroelectric capacitance plus C oxide capacitance. They collectively be positive, but this C capacitance can individually be a negative value. Okay. So to have a stable system, the net capacitance of the system should be positive. So this is the ferroelectric dielectric system, ferroelectric and dielectric. The net system will be positive, but the ferroelectric will be negative and the dielectric will be positive. But the net, this plus this net total system should be positive, otherwise the system will not be stable. So if you want to get a stable ferrofet, the net capacitance value should be positive, but individual capacitance value can be negative. So in order to make negative capacitance FET, see, TFET started in 2005. Negative capacitance started in 2015 and we are standing in 2025. So although negative capacitance FET is a newer concept, but still it has been more than 1 decade people are working on it. And what are the potential ferroelectric material here? Hafnium, zirconium oxide, or organic polymer like PVD, or lead zirconium titanate. Lead zirconium titanate, it is also ferroelectric material. There are three ferroelectric materials that were it is not only simulated, this is reported experimentally also. People have experimentally made it and reported that these three materials can be used for negative capacitance FET. Now the fourth and the final device for today's talk will be carbon nanotube transistor, CNT transistor. Structure wise, it is source is made up of metal palladium, drain is also made up of another metal palladium, and in between the channel is made up of carbon nanotube. What is carbon nanotube? This is basically graphite. If you want to cleave a single layer of carbon, you call it as graphene. But you know the carbon atom is having highest tendency to form bond. So these H carbon atoms and these H carbon atoms, they bond with each other, and instead of getting a graphene, you are getting a 3D allotrope of 1 atomic thickness carbon, right? Do not know whether I am audible or not, but
Ma'am, you are completely audible, ma'am.
okay, thank you. Yes. So what did I say in this thing? We are covering the fourth and the final aspect of beyond CMOS devices. Your source is composed of palladium, drain is composed of again palladium, and the channel is made up of carbon nanotube. I was explaining you what is the carbon nanotube. Graphite, and from graphite, if you are able to cleave a single atomic thick graphite, it is called as graphene. But cleaving this single layer of graphene is not possible, because these H carbon will bond again with these H carbons, and instead of getting a this plain graphene, you will get something. This is the plain thing, but this carbon atom will react bond with this carbon atom, and instead of getting a plain thing, you will get a tube kind of thing. And CNT is semiconducting. So this is metal, This is metal and this is semiconductor. And when there is a metal semiconductor interface, you call this junction as, what do you call this junction? You call this junction as Schottky junction. And this Schottky junction will result into this kind of tunneling carbon nanotube transistor. Like so, what is the basic governing mechanism for TFET? It was tunneling. For impact ionization, it was, for IMOS, it was impact ionization. For ferrofet, it was negative capacitance behavior. And for carbon nanotube transistor, it is Schottky tunneling, right? So basic advantages, it is having a better threshold voltage, lower threshold voltage, subthreshold slope is good, electron mobility is high. But what is the disadvantage? You do not have any mass production. Right now also people are using graphene for this, graphene for that, graphene for X application, Y application, but unless until you do not devise anything that can be used for the mass production. Why silicon is silicon? Because silicon industry is able to go for the mass production. We have scaled this production to such a level that the cost of fabricating a single transistor on an IC is same as cost of printing one letter on a newspaper. Because of this mass production, we are able to make that silicon technology so cheap. So if we are not able to devise anything for mass production of this carbon nanotube thing, your CNT FET will not work. Then as promised to you that these 4 transistors I have literally worked by myself. But apart from these things where I have worked on, there still exist many things that I myself have not worked, but still they exist. Like Valitronics is there, 2D materials research is there, molecular electronics is there. But still its bottleneck will be same. How to go for a standard mass production way. How to devise their potential interconnects. Then how to standardize those things, because everything has been standardized with respect to silicon. If you are changing the technology, you have to change the standards also. So these all are bottlenecks for it, right? When I devised this thing, I was standing somewhere here 2021-22, but right now I am standing in 2025 here, and this is the roadmap to go for next 10 years to 2035. We have gone from 2D materials, we have gone for opto things. One student of mine have gone through the neuromorphic computing, but the path is very long. You have to go for the electronics, you have to go for the phonon computing, quantum computing, molecular things, other organic things, then electronics work with the entropy thing. So as a faculty, if you want to explore something, why not to give these things as a presentation topic to your undergraduates, so that they explore it to some extent, come with their potentials, explain you those potential, and then you give it to your research scholars as a PhD topic. Now I will be comparing those 4 aspects. First was my TFET, second was my IMOS, third was negative capacitance FET, and the fourth was, I have written it as GFET. You can call it as CNT FET. GFET stands for the graphene FET. CNT stands for carbon nanotube FET. Yes, the basic operation principle is band-to-band tunneling, impact ionization, negative capacitance. Here it is ballistic, or you can also call flash tunneling. Subthreshold slope is minimum for impact ionization. But why am I not using it? Because its reliability it is having reliability issue. That is why I am not using impact ionization. The subthreshold slope is lower than 60 millivolt per decade. There is no hysteresis, but there is a small temperature dependence, and TFET is asymmetric. However, my NC-FET is symmetric. There is no reliability issue. Subthreshold slope is also lower than 60 millivolt per then 34.5 millivolt per decade. So the clear winner is among these four devices, which is the clear winner? Negative capacitance FET or ferro FET, or you can call it as hysteretic FET. There are n number of uh, uh, name there marked in literature, but negative FET, NC FET is the most potential beyond CMOS device among these four devices. Okay, so these all are my references, and thank you for your attention.
Thank you so much, ma'am.
So floor is open for the question answers thing. Yes.
Ma'am, I got some question. Actually, I restricted the audio videos, all this, just to maintain the
Okay.
discipline and all these things. I received a few
Yes.
questions. One of them is that the all kind of fates are available here: T fate, NC fate, G fate, all of them. These are the improvement in the actual fate. They were asking about.
These all are the means contemporary to the Fed. You cannot call it as improvement over the Fed, because if it is, it would have been the improvement. Then अभी जितने भी हमारे प्रोडक्ट्स होते हैं वो सब टी फेड पे बने होते हैं. तो ये सारे कंटेम्प्रेरी उसके कॉम्पिटिटर्स हैं, लेकिन अभी कोई भी वो आपके एग्जिस्टिंग सीमॉस को ओवर पावर नहीं कर पाया है.
Okay, the next question was the same which you have answered. Out of them, is any one of them is using practically in nowadays in devices?
Yes, negative Fed, NC Fed. Because it is symmetric, the only two additional steps you want, one is ferroelectric layer and another is metal. So NCFET is being used practically in the devices.
Okay. Okay, ma'am. Thank you so much, ma'am. I'll
Thank you.
request the participants. I'll share the email ID of Sangeeta ma'am in the WhatsApp group of FDP. If anyone wants to collaborate the research work with her, they can contact her.
Yes.
Is it okay, ma'am?
Yes, it's perfectly okay. So
Okay.
if anyone want to discuss anything, I am very much available on my email ID. My email ID is sangeeta dot singh@nitp.ac.in. You can write me your queries. You can ask me about my research thing. Uh, let's see how we can work together. Okay.
Sure, ma'am. Sure, ma'am. Thank you so much, ma'am. And I hardly
Thank you.
thankful to ma'am because she took a long time for us during her busy schedule. And I will definitely this session will helpful for all of the participants regarding the research and the industrial purpose as well. So thank you
The
so much, ma'am. Thank you again to be part of this
the honor
FDP.
is on mine to have me here. It is always I mean, I say it is always an honor to talk to young minds, because if you keep
Definitely, ma'am.
in
In
your
future,
9
we
to 5
will.
routine, you don't get something to research much. Okay, so the pleasure is mine. Thank you for having me here. Thank you.
Thank you, ma'am. Thank you. So, moving to the next session, we are starting the next
So I can
session.
leave now, right?
Of course, ma'am. Thank you so much again, ma'am. Thank you.
Thank you. Thank you. Thank you.
We are moving to the next session, and the next session will start by 7:30. So I request all the participants to get back before 7:30. We'll try to start at sharp 7:30 p.m. Okay. Thank you so much.